this manner. Oh, thanks. Thanks, Ruben. I forgot the recording. So if you load your transcripts and MFCCs in this manner, this will be roughly around 15 GB of RAM. Your Collab Pro has 25.5 GB, so this should very easily work for you. Even the previous approach might work for Collab Pro Plus, but this is much better. Just a question. Does everyone know why we have to do the phoneme string to integer transfer here instead of outside the loop? In the previous approach, we were doing the string to integer transformation of phonemes outside the loop at the very end. Here, you have to do it inside the loop. Any reason why? Yeah. So because we are creating an array of integer type, we have to do it here itself because we can't store strings. Strings might take more memory. Anything else in this slide which anyone has any question upon or anything that you, yeah.
How does it work?
Oh, okay. So basically your by default float in Python has 64 bytes or 4 bits. Sorry, 64 bits or 4 bytes. Integer has 32 bits. So 8 bytes and 4 bytes. So when you are moving from float 64 to 32, you are reducing how many bytes it takes to load the float value, and similarly for integer values. And if you simply calculate the total key value, multiply by 27, that's how many floats you had, which comes out to be a very large number.
Are we sure we can deal with it using a string?
Sorry? Oh, how did you make sure unsigned integer works?
Yeah.
Okay. That is simple. How many labels do we have? How many labels do we have in total? So transcript stores the labels, right? 40. So we have 40 labels, 40 or 42, whatever you see. And yes, so 2 raised to 8 is what? Right? So we can easily store 40 labels into 6 places. If we were using 32 bits, it would be 2 raised to 32, which comes out to be a very large number, which is like a lot of wastage space. Hence, we can reduce it down to 8 bits. Anything else about this? Does anyone understand why we, like, how we are progressing this CX and CY? And why we have to do that? So because we created a 0 array to begin with, now we can't append to the array. We have to store it at certain indexes. So we are capturing exactly where we stored it last time, from where to where, and then we are increasing it to the next time so that we don't overwrite anything. Any other question on this slide? All right, so this is how it looks like once you load it in the memory. So I'm using Collab Pro, and if you see, I've been able to load everything on 15 GB of RAM. So if anyone who's trying to load larger data in Collab Pro, you should be actually monitoring how much RAM it's consuming or how much GPU you're consuming so that you know which steps consume how much memory. And if it doesn't seem reasonable, you can actually try to, look further into it. For example, yeah, go ahead.
This is the entirety of Train 360.
Yes, it's entirety of Train 360.
Plus validation and test.
Plus validation and test. I'm not using Train 100 right now. So this has 360 validation test without 100. So if you looked last time when we were making so if you looked at your RAM consumption last time when you're using concatenate or padding, this RAM would go all the way to 40 GB. which is weird because our data set on our hard disk or our storage is just 20 GB. So because if our data on storage is 20 gigs and if in RAM it expands to 30 or 40 gigs, that means there is something inefficient going on. And hence that's how we figured out how to reduce it further. Does it make sense? Yeah.
How many entries are in the train?
Sorry?
What's the number of single entries inside the 360?
What's the number of what?
Of the single entries, like single data points. I can ask.
And yeah. And you have to multiply by this by 27 to find total number of floors. Anything else on this? Is like can everyone was everyone able to understand why we did this? Or why I was able to figure out that hey, we have to load data in a different way because our previous approach is not efficient. Okay. Okay, can someone tell why does the memory jump once I run this loop? Okay. So yeah, when we were loading the data, it only took like 15 gigs of RAM. But when I'm running my loop, so you'll have this kind of loop in your train function also, right? We can expand this. You'll have something like this in your train function. So when I'm running this loop and I'm using an input function to keep it running in that state, you'll see my RAM just increased to 22.4 GB. So it was 15 gigs earlier. Now it's 22 gigs. Can anyone tell why we have like where is this extra storage coming from? Yeah.
The data loader has multiple workers.
Yeah.
So like parallelly loading data from your main data set.
All right.
So that's why it's like shooting.
Okay, so we can try reducing the data loader workers down to 0. Not recommended because if you make it 0, your epoch time will increase a lot. But let's still do it anyway. All right. So we did reduce it down to like a few gigs because we removed the data loaders, right? It was earlier 22, 23. Now it's 21.9. So yes, every worker thread that you create will take some footprint over your memory, your RAM. So if you are running into RAM out of memory issues, you can try reducing your workers. Currently, I have workers at 0, which means all the data is loaded in the main thread itself, which is not recommended. But I'm just like, that's the minimum number of workers you can have. But you still have your memory as at 20 gigs, while your data was only 15 gigs. So can someone tell where the remaining 7 gigs are coming from? So you can see right here it's 21.9. Earlier it was only 15. And you'll have to do this kind of analysis to figure out how to load larger and larger data in your Collab Pro. So if you're using Collab Pro Plus, you don't have to worry about all this because you have 52 gigs of RAM. So you can be a bit inefficient and still get away with it. But if you're trying to load a large data on just Pro, you have to figure out where each gig is going and try to focus on your efforts upon how to make it efficient. So for example, what I suggest looking into, so this current implementation, which we showed here, this will work for Train 360. This will not work for loading Train 300 and 360 together. So if you try to use this approach for loading 100 and 360 together, it will crash. So you have two options. One option is your ablations should be run on toy dataset. Once you find some good models, run on Train 300. And if you find Train 300 accuracy going above 85 or 86%, save checkpoint and run it on 360. So that's how you're running the two datasets in sequence, and you won't have to worry about your memory issues. Second approach, which requires more work, is can you figure out how to load data in a more efficient way? So if you go to your dataset class, the get item part, yeah, if you look at the get item part, we are pretty much indexing the array, converting into a torch, and then batching it together into a single torch tensor. So this entire process of randomly creating batches is quite inefficient in terms of memory. That's where your 7 gigs extra are going towards. So if you want to make it more efficient, you might have to write your own collate function, or there's something called iterable dataset. Sorry. Okay. So yeah, what you can do is either write your own collate function in homework 0 part 2. You would have written collate function for yourself. So you can try that approach to create your own batches, or you can create something called an iterable dataset. So there also you'll decide how to make your own batch and try to keep it more efficient so that you are not losing that 7 gigs extra memory for your data loader. However, you should be able to cross 89% just at 360. So even if you're training a model only on 360, it is possible to cross the high cutoff. This is a medium cutoff architecture. Okay, before we go further, is this clear to everyone? Yeah. Sorry? You can try that. That will actually reduce your footprint, but it will also reduce your accuracy. Because your entire data is actually in float 32. If you reduce it to 16, you might not have that accurate results. Anything else? What? Sorry?
On this slide.
Oh, okay. Yeah. Which part? Okay. So in this slide, we are running through the entire dataset in 2 loops. This is the first loop, where I'm only going through the FCC files and trying to find a value for T. T is my all the time frames between T1 plus T2 plus T3, all add up to T. This helps me figure out how large should my dataset, the FCC array should be. So I'm using T, plus I'm using two context, plus I'm adding before and after all the calculations all together. And this is just 27. Okay. Same thing I did with transcripts. I use D, and now I have 2 arrays which are all zeros. I need to add values to these arrays. So previously, what we were doing was we were using a list, and we were simply appending to the list. So when I'm appending to the list, I'm simply adding the new values at the very end. But we don't have an end here. We have a single array here, so we have to add values inside the array. So Let's say this is 27. And this is P. So,
Why don't we have a list?
sorry?
Why can't we use a list?
So when you're using a list, your values are probably going to be float 64, 1. And 2, when you convert the list into array, you'll actually be cloning the data entirely.
Can't we have a list in the unsigned integer type?
So these options I'm using from NumPy, not from the Python's base class. And second issue is list does not have to be in a continuous empty space. Your NumPy arrays prefer to be in a continuous space. So everything from a list will be copied to a new location. So if you have 15 gigs of data, you will copy it and create 30 gigs of data. Which will crash your app.
Yeah. I agree with what you said, but after we concatenate the array, after when we have it as a list, the old list, that variable can be destroyed. Right?
Yes. So you can use GC collect right after that, and you might get away with it.
Right. So if I do that, I don't have to do this.
Yes. So that might still work. Just check what is your data value. If you're still storing integer float 64, that will still be inefficient.
Yeah, but if I do np.load of float 32, right?
Yeah.
Load it as 32.
So can you do np.load in your list or not? That's the check. Okay. Yeah.
Why are we loading table CCs twice?
So the first time I'm only calculating the value of t. I'm not storing this anywhere. I just need to know how big my array should be. And
But I not also is the right.
loading time, yes, but I only load the data once. So it doesn't increase my epoch time. Yeah.
So what I did is after I loaded the data, before I appended to this, I converted MFCC. And then I appended to this. So I still use a list, but it's a list of
No, so you can just check what's the data type inside the list, which might work, which might actually be 32. Yeah. Second issue that might happen in the scenario is list is not continuous. So it will be cloned, like you have 15 gigs of memory in a list, which is like spread across your RAM. You will find another 15 gigs of continuous memory for your NumPy array. And if that is not available, even though the previous one will be deleted, if that is not available, you might run into auto completion.
Yeah, I did run into autoscaling.
So even that's an issue. If your list is in a continuous space, it might be easier to convert it to a NumPy array without causing the out of memory issue. But then if you know how big your list can be, then you can just make this kind of thing. Any other question? Is this clear to everyone? All right. So you can load 360 in this manner in Collab Pro also, on a 25 page GCP VM also. The only issue is to load the entire accept, you have to do some extra work. Okay. I'll move to the media cutoff architecture. So last time, a few weeks ago, we released this. Is everyone aware of this as a post? And these architectures. Okay. So in my hackathon slide itself, I have these links. I would recommend everyone to just go through these links. These are about previous Piazza posts or content we have released, because I know everyone doesn't read everything. So one of these things were that we released the so we released low cutoff. I don't know how like 2 weeks ago roughly. So yeah. So we have like 16 different architectures. All of them will cross 80% on 2000 within like 1 or 2 epochs. This is just for anyone who is struggling to figure out how to move from very low to low cutoff. So the cutoff is 75%, but this will all reach 80% on 2000 very easily. And here are the parameters for it. So I'm using 2000. I'm using normalization, context, 20. Activation GELU, this is not a spelling mistake. I don't know if I write GELU and make a mistake. So it's GELU and yeah. And these layers are simply the width of each layer. So the input layer is 107, which comes from our context value. 40 comes from our output classes. Everything in between is what this layer architecture is. And this is a picture of how this architecture looks. there are 4 hidden layers, one input layer, one output layer. So if you implement this, you'll actually at least reach 80%. And many of these actually can also cross medium cutoff. So many of these will also cross 85% very easily on 300. So I just chose one. I actually chose something with just 4 million parameters. So this parameters here is because you have two choices. One is you train a very large model, close to 20 million parameters, and try to reach at the high cutoff in one go. Or you can train multiple small models, ensemble them together, and cross the high cutoff. So just to show that both the things are possible, you have some models with 15 million parameters and some models with just 1 million parameters. So you can have like 1 million parameters and see if it reaches a better cutoff. So I just took the second one and ran it through the entire data using this approach. All the parameters remain the same, only the dataset has changed. And I was able to reach 85% accuracy within 10 epochs. So the same models will reach 85% accuracy within 10 epochs. I don't recommend going this way because these models have not been tuned properly. They were just given for a sample. Ideally, you should be able to cross 85% on just 2000. So the strategy that I would suggest is so there are 3 kinds of data sets. One is a toy data set. Check the first slide of Hackathon to find the data set. Second is you have 2000. Third is 2360. So if you optimize your code properly, your toy data set will take just 1 minute per epoch. 2300 should take like 10 minutes per epoch. And 360 by this approach takes around 20 to 25 minutes. So what you can do is start your application with toy and test, like you can test let's say 100 models. 100 or 1000 connections because it all takes just 1 minute per epoch. So you can test 100 or 200 models for just 3 epochs. Find some 5-10 good models. 5 or 10 good models with parameters. Run these on 2000 and find maybe 1 or 2 good models. Save the checkpoint and then finally run this on 2360. So ideally, with this toy data set, you should be able to reach 71% accuracy, 70 or 71%. With 2000, you should be able to reach 85 to 87%. 87 is tough, 85 is very easy. So, but just with 2000, if you're not able to reach 85%, maybe you should look for a different model. Don't go to the 360. And 360 should be very able to cross high cutoff. So, any question on this? Yeah. So with 100, make sure your model is reaching 85-86% accuracy. So you will find 1 or 2 or 3 models like that, and then you can train those models on 360. So if you're doing ensemble, you can train 2 or 3. If you only have 1 large model, just focus on 1. Any other question? Yeah.
So when you're finding a good model for the let's say for the dashboard data set, and then you're increasing the data size, wouldn't we need to like fine tune the model? Like some things might need to change for it to train on say 100.
Yeah. So some things you might have to fine tune, but ideally, if your 2 models are performing, like 1 model is performing better on toy, that model might also like high likelihood of performing better on train also. So I would say tuning on toy first is better simply because it takes less time. Because it only takes 1 minute, so you can do like 1000 experiments in 1000 minutes, and then just focus upon the ones which work well. You might have to do some tuning on 100 also, but that would be like minimal. And you should not be doing any tuning on 360 because 360 takes a long time. What else? Okay.
One epoch is 360 days, like half an hour.
So if you're so to increase you can try increasing batch size. So after you have done the mix precision and you have done all this, everything else that we discussed before, batch size is something. If you increase batch size, your number of batches will reduce. So your per epoch training time will reduce. But increasing batch size has two issues. One is it will increase the GPU memory. The higher the batch size, the more GPU memory it will take. For this homework, GPU is not an issue. So no matter how large you make the batch size, GPU will not really be a problem. The other problem is if you increase batch size, your accuracy might suffer a bit. So you have to actually just check different batch sizes and see around which range you're getting a good epoch performance, like a good time per epoch, and also a good enough accuracy.
Half an hour is not bad.
Sorry?
Half an hour is not bad.
You can make it 25 also. Like half an hour is not bad, but you can make it 22, 23 also.
When you increase batch size, what happens?
So if you like, this was covered, I think, in last week Tuesday lecture, that why do we even do mini batch in the first place? So whether you do your gradient descent on the entire data or on a mini batch, why would mini batch is better? So you can review the lecture for that. Yeah.
Right now, my one epoch thing that goes for around half an hour.
100 takes half an hour.
Okay, just changing into you will 8 megahertz or do I need to change 20%?
Half an hour. How much is your batch size?
10, 28, 22.
Okay, there's probably some other issue also. There's half an hour is too large for, and you have implemented mix system, right? Are you using mix system? You should use that first. What else? Any other question on this? Yeah.
Yes. You mean that you say that you can use the train data set for how to reach the accuracy?
Yes, you can reach 85% very easily on training. Test accuracy, yes. The accuracy on Kagan.
I just reached 8. So what do I do? It doesn't match.
Yeah.
How can I reach 8?
So you have to find more models. So the models that we shared on spreadsheet was just for as an example. You have to try different combinations on toy data set. So if something is reaching 70% on toy, it will reach around 85% on it. So every data set has its own validation. So toy has its own validation. You have a different value for toy, and you have a combined validation for each. So if you check the recitation 1C, the Piazza Post notebook, you'll find toy dataset. It is also in the Piazza Post 221 for network architecture search. So both these posts have linked to the toy data. And recitation 1C also has code for how do you do machine learning on Libri speech. Okay, so this slide is like already available. This is from previous hackathon actually. And I'll share this slide again so that you can just find these links easily. Yeah.
Just count that toy data set of Google Colab. We just like use the same hours and we just use the same drivers and between that. I'm just saying that, so we're just using the Google Colab with the toy data set and we just use the same, we just find the best one.
And it's the best parameters, yes.
And then just use the same, it's obviously
1900, yes. The slight caveat, the toy dataset has 26 frames. And this has 27 frames. So you might have to change your code slightly. So just make sure you are not making this mistake. The rest should be same. And you might have to fine tune a bit on 1900. Change the parameters a bit here and there. And then once you find the like perfect thing, just go to 360. And you can actually, whatever checkpoint is stored here, you can load the checkpoint and then train up 360. So you don't have to start from scratch. Once you find a good model here, you are storing checkpoints also, right? Load the checkpoint and then train 360.
after all these talks.
After you save your best performance checkpoint, that's checkpoint. then load it, and then anything else? Sure.
You see, this data loading is compulsory for us to achieve.
So this is actually primarily for loading 360 on Collab Pro. So if you're using Pro Plus, loading data should not be useful for you. You do need to train on 360 to reach 87%, to reach 89%. Yes. So reaching 89 or just training on 100, probably I'm not sure if it's like doable. But with 360, it's easy. So this approach can help you use 360 very easy.
And how many blocks would you say we should train on 360 to reach?
I would say when you're on 360, train till you reach convergence. So by convergence, you mean like your models will like back to convergence.
Yeah.
It will not exist anymore. So you can stop.
So right now I'm using a diamond. It's kind of cylindrical only because there's not much difference there. It's still a diamond. And on train 100, I'm reaching 80.
Okay.
So now I'm moving to train.
I would say try a bit more combinations because on train 100, you should be able to reach 85, 86.
Validation accuracy.
Validation accuracy, yes.
The diamond is not the.
So it's not about diamond, it's more about you have to try different parameters, increase and decrease the length of the architecture.
Okay, I should just talk to you later. I tried so many things.
So try things as a group. You don't have to do everything, like do all the experiments alone. You have 4 people.
Yeah, we are doing that. But
Okay.
so if one person's thing works, is it okay if we pick that architecture?
Yes, you can pick the architecture and your hyperparameters from your group. Your code should be different. So you should not have the same code.
Yeah, but like it's just building the.
Yes, so you can have the same exact width of every layer. You can have the exact same parameters, but how you implement your dataset class should be your own work. You should not copy paste your entire classes together. What else? Any other question? Those who don't want, like those who are not using Collab Pro, you can also use Google Cloud Platform. There might be some issues based upon the limits because if everyone is using the same zone, you might not find a VM Collab using Google Cloud. So just try to change the zone and region and see if you can get a VM. Even Cable allows you to have around 30 or 40 hours of notebook running time on a GPU. So you can run the same Collab notebook on Cable and see if you can use free. Any other question? Yeah.
Yeah, this is about like a basic intuition about the architecture. So in a sense, if I have these 2 layers considered, if the first layer is smaller than the other, the width is smaller than the other, versus if the first one's layer, the width is bigger than the second, what difference is there in the information that's transmitted?
So in general, whenever you are reducing width, you might lose information. This is a possibility. So, so you just have to see like if you're reducing width, for example. So maybe you can avoid adding dropper if you're reducing it too much, and try not to have a too drastic a bottleneck.
So the problem is assuming something like a reverse pyramid, where we keep growing the width. At the final output layer, it should be something like 3,000 neurons.
40.
So that's like really bad, right?
Yeah.
So does that mean we should avoid doing those kind of architectures?
You can try those architectures if you are facing issue with, let's say, vanishing gradient. If your gradient doesn't like pass, so you can look into residual connections there.
Right.
All the residual connections make more sense at the beginning, not at the end, but you can still explore.
Right. So when you say it loses information, it also means that if I have a very high width layer and then followed by a low width one, the gradients cannot propagate properly because the influence of each neuron is smaller.
Yeah, there might be, but but yeah, like at the end of the day, you'll have to experiment and see what makes sense. You can also see like where exactly your model is not performing, like which phonemes your model is struggling on, and
So
try to see.
one case where it is a cylinder. I had large norm and dropout.
Okay.
And the accuracy.
I'll just probably end the presentation and come to you. So, is there any other question about the slide? Is anyone facing issues loading the print clean 360 data? All right.